So we are going to start on this part, which is integration. Okay, so it's a very important. In fact, this is what is one of the reasons why. I mean, main reason why this measure theory is a subject that you learn. So for probability and functional analysis, this integration theory is the most important. So it's you can think of this entire like your basic real analysis, a parallel, but in a slightly more advanced setting. Okay, so you had integration there, differentiation there. We can have integration here and differentiation here. The integral is more general than that, and the differentiation is also going to be more general than that. But to be honest, so for if you are not into analysis, if you are not going to be in analysis, then by and large you will be happy with this integration theory. This is what you need mostly. But if you are in differentiation theory is also nice and useful. It is what is called geometric measure theory. It is a very interesting subject. If you study fractals, like things like Cantor set, Sierpinski gasket, and all that fractal objects, then the differentiation theory becomes very important. But what everyone sort of needs, and which is why this is a subject in, core subject, is this integration theory. Everyone should know Lebesgue integration, and this is useful in both probability and functional analysis. So in probability, there is something called expectation of a random variable. That's exactly going to be this Lebesgue integral, nothing more, nothing less. It's exactly Lebesgue integration. Okay, so that's what how it features in probability theory. And in functional analysis, I had indicated to you earlier, the problem with the Riemann integral is the natural spaces of functions you define using Riemann integral turn out to be not complete. Whereas with integration, Lebesgue integration, they will turn out to be complete. So this is Lebesgue integration. Okay, so this is what we are going to learn. So this is actually the most important thing that you must learn. Okay, and let me say it again at the cost of repeating it maybe the 10th time, that this is a point where people can jump on again. So if you all you need to know at this point to follow what this integration theory is, what is the definition of measure space? Okay, so in other words, what is sigma algebra? What is a measure? Pretty much, if you know that, and some basic definitions like pullback of a set, all that stuff. I mean, measurable functions. So that you need to know. Other than that, you don't need to know anything. I mean, the construction of Lebesgue measure is not required to understand for this one. So this one is you can take it as an abstract thing. We will define whenever you have a measure space, we can define integration of measurable functions on that space into real numbers. So that's what we are going to do. And the all that we did so far is actually basically showing that there are actually interesting measure spaces. So this whole theory is not some vacuous thing. Okay, so that's how you should understand it. Okay, so let's now start on the subject. Okay, so the basic objects, we have X, F, and mu, a measure space. Okay, so we have a measure space. So what we will do is we will take, so the goal is define integral of functions which map X to real numbers. Okay. Of course, we can't do it for every function of as large a class of functions. Now let's say just a large class of functions f. So we want to define integration with respect to, so this is going to be with respect to the measure mu. If you take real line with the Lebesgue measure, so when x is r, f is, you can take Borel sigma algebra or Lebesgue, you can take either, and mu is lambda 1, that's how we write it. So this will be a generalization of Riemann integral. So when I say generalization of Riemann integral, everything that used to be integrable will be, but many more functions will be integrable when we complete this theory. Okay. So this is something that you should keep in mind. This is where we are headed. We are headed towards a more general theory than Lebesgue measure. I mean, then Riemann integral. But there will be many other nice side fallouts of it. Okay. So that maybe we can remark later. Okay, but main thing is that it will be a theory of integration when restricted to real line with Lebesgue measure. It will be something more general than the Riemann integral, and that's the most important point. Okay. Okay, so we'll come to that later. The specialization, the general definitions, everything is very. One can do it in full generality. So the advantage of doing things in full generality is you get rid of unwanted features. So when you take real line has so many good properties. It's a vector space, it is a group, it is a field, it has a complete metric space, everything. So when you work with specific structures, it is always a distracting thing. You don't really realize what features of the space are actually being useful. So generality, the purpose of generality sometimes is to clarify what exactly you're using. So that's why we'll work with just this. There's very little structure. So measure space, you remember, not much structure. This is just a set. X is just a set. F is a sigma algebra. That is a collection of subsets of X closed under complements and countable unions. And mu is a countably additive function on F into positive real numbers, including infinity. Because countably additive means when you have disjoint union of sets in F, then mu of the union is the sum of the measures of the thing. So that's all we have. Okay. So how are we going to define this? So first of all, the simplest, so it will go in several steps actually. The integration definition itself will take us a while to get to the definition because it is not just a simple definition. I mean, even with Riemann integral, you remember there is a limit operation involved. You take upper sums, lower sums, then if they match, then you take upper sums, lower sums, and take a sort of lim inf and lim suf, and if they match, that common number will be called the Riemann integral, right? So something like that, a limiting operation is necessarily required. So it will take us a while, probably this lecture and the next lecture, to complete this theory, but we will do it. Okay, so what we can start with is, we can start with when f, so let's take, so this is what we have. If f is indicator A, where A is an element of this sigma algebra, then we shall want its integral to be just the measure. Its integral, so let me just write its integral to be mu of A. That's what we will want. If you take the indicator function of some set, so X is here and A is just a subset of it. So if you want a function which is 1 here and 0 outside, then its integral, we would like it to be the measure of that set. Okay, see, we are saying, a point to make here is that we are getting to a definition. Now, what makes, so in a book, a definition is just given and you accept it. But really, but definitions are not the starting point. I mean, they are actually the end points of a lot of thinking, actually. What is the correct definition? This is one of the most subtle points in mathematics. So, good definition is worth more than many theorems, in fact. So, but we should have in mind what is it that we want. I mean, what is integral? Okay, so we are saying we want an integration. What the hell is integration? What does it mean? Okay, so is there any requirement we have in mind? Well, yes, there is, but I will not tell it beforehand. But one of the things is that it will be this. Okay, or maybe I will even tell what is integral actually. What is it that an integral? So to functions we have to associate numbers, right? So to functions, you have to associate numbers. What would you call it? When would you call it integral? Suppose I have a class of functions, and for each function, I will associate some number. Okay. What properties would you like it so that you will call it integral? Well, you know only one integral, so maybe you can't answer that question, but let's float it anyway so that you have a moment to think about it. So what is it that we should be called an integral? Yes, anyone? You can venture an opinion. There is no harm.
So some form of a essentially a generalization of a sum, if I were to just think of it very crudely.
That is
So if we associate
a very good point. Yes, all integrals will be like actually somehow sums. I mean, integrals are analogous to sums. It's a very good point. It's an excellent point. In fact, any integral that we define will be actually using sums and some sorts of limits. That's what it is going to be. That's actually one of the things I did not mention here. I said I'll say there will be some other fallouts. Sum and integral are always analogous. Even with Riemann integral, everyone is aware of that. That Riemann integral is somehow like a generalization of a sum. In some way, you're adding infinitely many things in some sense. But Lebesgue theory is a nice one because we are doing it in this level of generality. We'll see that not only is it analogous to a sum, actually sum and integral will both be special cases of this Lebesgue integral. In fact, they will be both put on one common footing, in fact. So what you say is a very good point. Any other perspective on what should be an integral?
The inverse of a differential, maybe.
Okay, that is also a good point, but we are not starting with the differentiation. So it would be a good thing, better to independently do the define integration and define differentiation, and then see that they are actually inverse operations of each other. See, two things have to match in mathematics. Two things have to match to make a sort of theorem. So fundamental theorem of calculus, which says that derivative is inverse of integral under some conditions, only makes sense after you have a definition of integral and the derivative both. So we have to develop a differentiation theory and integration theory, and then they will turn out to be sort of inverse operations. This is a good point, but it will come later. Any other perspective? So ultimately, we know what we want. We have a collection of functions. We don't know how large that collection is. We would like it to be very large. To each function in that collection, we will associate a number, which will be called the integral of the function. So what is it that we want out of this thing that makes it an integral? So this is so don't, okay, so maybe I will just mention it, but don't worry about it too much. It will be justified later. Basically, at the end, it will turn out integral is just nothing but there are two properties, linearity and positivity. That's all that is required. As we will go through this, we will see. But maybe as we go through it, first we will see more in the sense that Sheikh has said. So that we will go from sums to limits and get to integral. Okay. So the other thing that I said, integral is nothing but a linear and positive functional. That's a theme that we will see again. We will see very much. Okay. So let's now take it. So what we would like from what I said is that, so we will make a definition. Okay. So if I have indicator A plus indicator B, okay. So suppose I have two sets A and B. Let's say disjoint. So what would you like to be the? What should its integral be? Okay. What should its integral be? Well, we would like it to be mu of A plus 2 mu of B. This is the linearity sort of we have in mind. Okay, so that is going into the definition. All this is just motivating. That's all. So this is how we will start. We will for functions which look like this is how we would like the integral to be. For indicators, it is clear. And if you have a simple representation in terms of indicators, we know what we want it to be. It will be like this. If it's a linear combination of indicators, we would like it to be this. So that brings us to the first definition. Any questions?
Yes, sir, my internet dropped. Could you please repeat
Okay. So from
what
what
did you say about the about integration? You said there are two things to check. Something like that.
No, I was just asking. So we are making a definition of integration. I said then we have to have in mind what we want out of integral, right? If that is the case. So what is it that an integral is supposed to satisfy? So this is a bit like asking what is it that a measure was supposed to satisfy. We saw that volume, we would like it to be additive. If you have two disjoint sets, you want the volume of the sum union to be the sum of the volumes. That ended up in our giving up the notion of volume for all sets, etc. That's fine. So, but similarly in integration, what is really at the back of our mind is two properties, which will come again and again. At the moment, don't worry about them. They are linearity and positivity. I will tell you what they are when we get to it. But that is what an integral is going to be. So anyway, what I am saying now is you can forget all that. So for indicators, we would like the integral to be the measure of the set. And if I have some function which is a kind of linear combination of indicators, I would like the integral to be the corresponding linear combination of the measures. Okay, if I have indicator A plus 2 indicator B and AB are disjoint. Here, AB are disjoint. Then I would like it to be mu of A plus 2 mu of B. Okay. So with that in mind, I make the actual definition. This is all just motivational speech. So now I have the actual definition. So let's make a definition. So let's call such functions simple functions. Okay. The function f from x to r. Okay, here I don't put r bar. Let's not allow infinity minus infinity for simple functions. Okay, is said to be simple if actually I can allow r bar also, but okay, let's not worry. Let's leave it as r. If the range of f is a finite set. That is, f takes only finitely many values. Okay, f takes finitely many values. So that is called a simple function. Actually, since I'm never going to use anything else, so let me just add a little bit extra here, a measurable function. Or maybe no, maybe I leave it actually, so that we are clear. A function f is said to be simple if range of f is a finite set. So what does that mean? So, well, we can elaborate on that definition a little bit. So say range of f is, let us say, a1, a2, and an for some n, for some n, and for some ai's are distinct. N has to be greater than or equal to 1. There has to be at least one value, and ai are real numbers distinct. Okay, they are distinct real numbers. So then, what we can write f. So how is this a linear combination of indicators? Well, by definition, it is taking only these values. So if I take my set x, there is some region on which it is equal to a1, right? So this is where it is equal to a1. Somewhere else it's equal to a2. Somewhere else it's equal to a3, and so on. So let's write that. So let's write those sets. So let a1 be f inverse of the singleton a1. So where it takes the value a1. So that could be a set like this. So it is the set of all x in capital X such that f of x is equal to a1. And so on. we define A1 up to AN. AN is F inverse of the singleton AN. Okay, so these are the sets. So this will be a partition of. So then AIR pairwise disjoint and the union is X. Okay, I hope that is very clear, because you can't have a point in A1 as well as A2, because if X belongs to A1 and X belongs to A2, then f of X has to be small A1 and f of X has to be small A2. But these are distinct, therefore they can't be the same. Therefore, these are disjoint. And also for every X, f of X is one of these values, right? Range of F is just this. So whatever X be in the space, its f of X will be one of little a1, little a2, little an. Therefore, the union has to be all of X, because fx is one of those values. Okay, so this is what it is. So we can, because of this, we can write, hence, we can write F as small a1 times indicator a1 plus small a2 times indicator a2 plus small an times indicator an. Here we can write it like this. Is that clear? Because what does this mean? F of X will be small a1 times indicator a. If X belongs to exactly one of these, so if X belongs to a5, then all the other terms will be 0 and you just get small a5, right? Small a5 and so on. So this is the F has this representation. So this is what a simple function is. I have defined it as something whose range is finite. Equivalently, we can say that F is of the form this one, where so simple functions are of this form where AIs are distinct real numbers and capital AIs form a partition of X. Okay, that's what simple functions are. I hope it is clear. And for simple functions, we know how to do. We will now define integration. So let's maybe give a name. Right. Okay. But another small point. So when is this? So how would you define the integral of this? We would like to define it as small a1 times mu of a1 plus small a2 times mu of a2 and so on. But can we apply mu to a1? Only if that capital A1, that set, belongs to the sigma algebra. Otherwise, mu of that set doesn't make sense. So this is important. So here is a small observation. So F is measurable. So it is clear what measurability here means. F is from X to R. On X, we have the sigma algebra F. That's not going to change. And on R, we have the Borel sigma algebra. So F is measurable with respect to those if and only if each of these sets is measurable A1, A2, AN all belong to the sigma algebra. Okay. So why is that? I mean, that is very easy to see. We saw that we have seen before that indicator A is measurable if and only if A belongs to the sigma algebra, right? So let's say this way. So I will not write a proof because it is trivial. Let's say this way. Suppose each A1, A2, AN belong to the sigma algebra. Then indicator A1, indicator A2, indicator AN also belong to the sigma algebra. And if you multiply them by some real numbers, they will belong. And if you add measurable functions, that is measurable, right? So sum of measurable functions is measurable. Yeah.
I kind of lost you for a minute there. Indicator is measurable in what sense?
It's a function,
Oh,
right?
as a function. Right. Got it.
Yeah. So indicate. So what I said was if AI in F imply indicator AI from X to R are measurable. So linear combinations we have seen of measurable functions are measurable. So this is certainly clear. So if these are measurable, then f is measurable, this f. Conversely, if I want to see the converse direction, that's from the definition of measurable function. So if f is measurable, then inverse image of any measurable set should be measurable. And singleton is a Boyle measurable set, right? Singleton is a Boyle measurable set, and inverse image of that is also has to be measurable if f is to be measurable. So both ways it is clear. So measurable functions, simple measurable functions are exactly those. So just to put down the point, so f a simple measurable function on x is one of the form. Say, while the integration theory lasts, my measurable functions will take values in real numbers or extended real numbers, okay? Not into other spaces. So that is important. So here throughout now measurable functions will usually mean into real numbers unless I say otherwise. So a simple measurable function on x is one of the form summation ai indicator ai capital AI I equals 1 up to n for some n greater than equal to 1 distinct a1 a2 an in R partition a1 up to an of x with each ai in f for all I equals 1 up to n. Okay, for all I it is so a measurable partition is what the word sometimes used, meaning that the individual pieces in the partition are measurable. Okay, so a measurable part, you have a measurable partition and some distinct real numbers, and you take the value a small a1 on capital A1, small a2 on capital A2, and small an on capital. That's what a simple measurable function is. So for that we know what the definition ought to be. Okay, so now I will define the integral, which is
it's 4 o'clock.
So this is a sum. Okay, this is a sum, like Shekhar said. So here, this is how we define the integral. The integral will be sum in this case. And it will form the basis for us to define integrals for more general functions. So if f from x to r is a simple measurable function with representation f equal to a1 indicator capital A1 plus an indicator capital An as above. Let me write as above, meaning I'm not writing all that. So capital AI's form a partition. So as above refers to this. Capital AI's form a measurable partition and small ai's are distinct. Then its integral is defined as a1 times mu of a1 plus up to an times mu of an, capital A. Okay, and the notation is integral f d mu. So this is notation. This is just a notation. We will read it as the integral of f d mu. I mean, you can write it as integral f d mu over x. Okay, or if you want to read it out in words, integral of f with respect to the measure mu over the space x. So alternate sometimes it becomes important to write a dummy variable there, like we do in Riemann integral, fx d mu of x, where this x of course doesn't, I mean this x doesn't mean, this capital X matters. It is telling where you integrate. This one, it is nothing. I mean, you can write anything here. It's not small x means you write anything you want there. Okay, so any dummy variable will do. You can write. Okay, so that is just a dummy variable, which means nothing. Oh, sorry, that's wrong. It should be the mu of this figure. Okay, so those are that is the definition, okay, of the integral. Now from here we have to take it up to other levels. But what happens is that the thing is, it will not be so obvious how to define it. So maybe I first define it, and then we'll see that we have to prove a few things here about this integration on simple functions first. Only then we can go to then we will be able to extend it to other functions. Okay, so but let me try anyway directly to yeah. So which way should I do? So yeah, so let's prove some properties here. Otherwise, it will be problematic. Okay. So some books. Okay, I didn't introduce any symbols. So many books. Okay. Yeah, actually, there is a slight problem with this definition. Okay. So can anybody see a problem with this definition?
Well defined as no, actually it is well defined, right?
It is well defined because I'm using a specific representation. Some of you may,
Right.
yeah, so I will come to that. What if I represent, f can be represented like this in a different way, possibly, but not, I mean, not with this, but with just looking at this. Yeah, but whether it will still be valid is a good question. We'll come to that. But a simple function has a unique representation like this, because this is a, I take the range and then I take the pullback of each of the values in the range, and then I write it like this. So this is a unique representation. So well-definedness seems okay, except one problem. So measures can be infinite. That is a problem. So I didn't say anything about my measure. I didn't say it's a finite measure or anything. So it can happen that measure is infinite. That also is directly not a problem, except that suppose A1 is 1 and A2 is -1. So, and both mu of A1 and mu of A2 are infinite. So then there will be a problem, right? So suppose you imagine, suppose I have indicator A1 minus indicator A2. If mu of A1 is infinite and mu of A2 is infinite, then what am I talking about here? Then I am defining the integral to be mu of A1 minus mu of A2, which is not meaningful. At least if one of them was infinite, the other was finite, I could define it as plus infinity or minus infinity and get away with it. But this doesn't make any sense. Infinity minus infinity, no way to make sense of it. So this is a problem. So I will just restrict myself. Okay. So what I will do is, so let's make it to R plus. R plus means zero infinity, zero included. Okay, this is not any, is a non-negative simple measurable function. Then I define like this, and this is possibly equal to plus infinity. Okay, so here nothing, all the AIs are positive. Okay, so with AIs as above, but now AIs will be positive. Okay, so notice AIs are greater than equal to 0, because the function takes only non-negative values, so each AI is non-negative. Therefore, there is, and mu measures are always non-negative. So this linear combination could be plus infinity, which is a value in 0 to plus infinity included, because one of them could be infinity, and if a1 is 1, so for example, if you are in the real line and I take the constant function 1, that's the indicator of the whole real line, then I am getting 1 into mu of r, lambda of r, that is infinity. So I allow this value to be plus infinity also. Okay, so that's all right. So we don't why that is not ambiguous, at least. Is it okay now, the definition? Okay, so let's define it only for non-negative measurable, simple measurable functions. Yeah, so some people use the following notations. So I don't know if I will need to use it, but some books will use fairly common notations. Let's say it's not any universal notation. If you want, you are welcome to use it. Script S for collection of all simple functions. Simple measurable functions. On, I mean, the space is assumed to be fixed. Okay, simple measurable functions, and S plus is used to collection of all non-negative simple. Okay, when I scroll like this, is it clearly visible? I mean, are people watching on cell phone and so on? I mean, sometimes I tend to do this, put things into a corner and do a scroll in a small font. Is that usually visible, or do people have problems with that? Anyone?
So on smartphones, people can actually pinch to zoom, and on laptops, it's not a problem.
Okay. Okay. Yeah. Okay. So you can zoom the screen yourself, right? Okay. Okay. That's a good point. Yeah. So then, so yeah. So on board is the worst. So yeah. So this is so these symbols are used, script S and script S plus. Anyway. So here we have defined for f in script S plus only. Okay. So we would yeah. So that's enough. Anyway, we will have to go further steps. So now we need to go further. We will use this to define integrals for more general functions, but we will need certain properties here. Without that, we will not be able to go forward. Okay, so we will need some properties. Yeah, maybe
Sir,
I will.
I have one small query.
Yeah.
Sir, here if mu a1, mu a2 all are like within 0 to infinity, infinity is not included, plus infinity is not included, then how can it be 0 to plus infinity? Because all these are finite terms, right?
Yeah, so it will be some number, right? This
Yeah.
plus infinity doesn't have to be plus infinity.
Yeah, like that should not be, then plus infinity should not be included, right? Like
why not? I mean, it is allowed, that's all. You don't have to use it.
So maybe later on when we extend to countable sums.
No, but mu of A is need not be finite, right? I mean, they don't have to be finite. Even with finite sums, I am not saying the measure is a finite measure.
Oh, right.
So it can very well be plus infinity, possibly. I mean, plus infinity means it is possible. It doesn't have to be. I mean, it can take any values here. Oh, maybe I didn't understand your question. Can you repeat again?
Like mu of a1 can be plus infinity?
Yeah, it can be. I mean, it depends on the measure. I said it's a measure space. Measures can be infinity. For example, Lebesgue measure. In Lebesgue measure, so if we take for example, so let's just write a simple example. So with the real line Boyle sigma algebra and Lebesgue measure, I'll just write lambda instead of lambda 1. So I can take indicator of 0, 1 minus plus 2 times indicator of 1 to 2 to 7 or 1 to 7, let's say 1 to 7 minus plus indicator of 7 to infinity. So for example, this is a simple function. By the way, this also includes 0 times indicator of minus infinity to 0. So this is a simple function. Okay, it takes 4 values, 0, 1. Actually, it takes the value 1 on 0, 1 and 7 infinity. You should club them. So maybe I just make this 3. Okay, so it takes 3 values, 0, 1, 2 and 3, and it takes it 0 on this set, 1 on this set, 2 on this set and 3 on this set. So if I calculate the integral, I'll get if I calculate the integral, I get infinity because this one has an infinite measure, right? So this one will have integral is infinity. So if f is this, then integral f d lambda is plus infinity. On the other hand, if I take a function g, which is, let's say, indicator 0, 1 plus 2 times indicator 1, 7, let's say just this, and 0 outside, which you can write as, if you like, 0 indicator minus infinity to 0 union 7 to infinity. Okay, so this is a function, so its integral is something finite. Integral g d lambda over r will be, this will be 1 times 1 because that's the measure of 1, 0, 1, and plus 2 times the measure of this will be 6, and that's all. So in 0 times, okay, 0 times infinity. Okay, maybe this is a good point to say the convention. 0 times infinity is to be interpreted as 0. So this will give me 30. So 0 times infinity interpreted as 0. Okay, so this is a convention. So is it clear now that function?
Yes, sir. Thank you, sir. Got it.
So this can be finite, can be infinite, but it's okay. So that's why I did not allow both positive, negative. Then I get ambiguity. So if I had a positive value on one set of infinite measure and negative value on another set of infinite measure, what should I do? It's not so clear. So I don't define that. Maybe I will give you the entire definition of Lebesgue integration, but it will be only fulfilled when we figure out the properties of it. Okay, so instead of stating the properties here, let me give you the full definition. Okay, which will go in 3 steps. This is step 1. What we have done is step 1. Step 2 is what will come now. Maybe I choose a different color. Okay, so this is step 1. So step 2, Lebesgue integration will be defined in 3 steps. Okay, so first simple one is for non-negative simple functions. Simple and measurable. Okay, I should write. The way I define, many books will define simple functions to be already measurable. I didn't do that, so I'll write simple measurable function. Okay, so now the second step will be for general non-negative measurable functions. Okay, so not any more simple. Okay, just non-negative measurable functions. So how do we define that? Okay, so I'll give you the full definition, but as I said, thing will be only complete when we understand the properties. Okay, so if suppose f is a measurable function from x to r plus. Okay, x is to r plus is measurable. Then we define its integral with respect to mu as integral over x f d mu, which you can write with all these notations, f of t, d mu of t, whatever you want. is defined as, this is the definition, as the supremum of integral, let us call it phi d mu over x, where what is phi? Phi is non-negative, simple, measurable. So for that, the integral was already defined in step 1, right? So this is the integral from step 1. Actually, yeah, so I will come to that. So, and it is not more than f. Phi less than f. So you take any simple functions which lies below f. Okay, it's already non-negative. Non-negative, so 0 between phi is sandwiched between the constant 0 function and f. You take any such simple function which is measurable. You take its integral, which was this integral was defined in step 1. Defined in step 1, and take the supremum over all such phi. Okay, all such functions, that will be defined as the integral of f. Okay, so that is step 2. So do you see any slight issues here? I mean, so what is it that you would worry about if I gave this as definition?
Supremum might be infinite.
That is possible. We allow infinity. We allow plus infinity as a possible value. Good, but it is a point which is well taken. So this is possibly a value in 0 plus infinity. One thing, okay, that reminds me, supremum can be problematic. Supremum being infinity, I allow. Supremum can be meaningless if the set is empty. But this set is never empty. Why? We have the 0 function, for example. You can take the constant function 0, that is always there. So this is not an empty set. There's always the 0 function. So the number 0 is here, because the constant function 0 is a simple function whose integral in the first definition is 0. Therefore, it will be 0. So this is well defined. It will be a non-negative number. So it will be a number between 0 and plus infinity, both included. But something else. So, yes, anyone? Look at both step 1 and step 2. Maybe something.
You might not. Oh, no.
Yes.
No, nothing.
Yeah, you can venture answer here.
I think Umang had said something related to the existence of the supremum, right?
Yes. So, no, I mean, he said the supremum could be plus infinity. Even if all these numbers are finite, the supremum could be infinity, which is allowed. I allow plus infinity.
Oh, right.
What I said was that if that reminded me that I should point that if the what is supremum of empty set? Okay, it doesn't make sense. We often define it to be minus infinity, but here it is never.
It is a non-empty set, right?
Yeah, it's a non-empty set because 0 function is there. Yeah.
This is essentially your analog of the lower integral, the lower step functions of sorts.
Yes, in a way. Yeah, I will come to the how it differs from Riemann. In some ways, it looks like Riemann integration if you see the analogy that you are saying, but in what it is crucially different in some way, which I will come to later. We'll talk about that later. But there is something, I mean, just as the logical point in definition, there is something a bit problematic, right? Don't you see? See, suppose f is I use the same notation here, okay, the integral. Suppose f is itself a simple function, which is non-negative and measurable. Now, there is one definition here, direct definition. But here is another definition as the supremum of functions which are below that. Are they exactly the same?
That will have to be, right? Because then f itself will belong to that set phi.
Yeah, but still, okay, so but we haven't proved those properties. So one of the properties that we here is that if f1 is smaller than f2, then the corresponding integrals are in the same order. Okay, this is what I was talking earlier about positivity or monotonicity. So that is true here because mu is a positive measure. So which is important. If mu was allowed to take positive and negative values, okay, measure for us is always taking positive or non-negative values. If measure was allowed to take positive and negative values, there would be all sorts of problems. But because that is not the case, this has this monotonicity property. So this will bring us this. But I'm just saying that these are things one has to verify, which is why between this step and this step, a few observations will have to come. Okay, but as I said, let's see it in one shot, and then we will go and elaborate on all the things. So, but this will be well defined and everything. Okay, so this will be well defined and all that. And third step, how I don't want to only integrate non-negative functions, right? I want to define third step. General measurable functions. Okay, we won't be able to define it for all measurable functions. So suppose f is, so this is also a definition. So let me write it like that. Suppose f is a measurable function. How am I going to define its integral? Okay, so it's not necessarily non-negative now. That's the only difference between this step and previous step is that the function is not necessarily non-negative. So what we do is we'll try to find non-negative functions. We'll try to write. So then we'll define the positive and negative parts. What is positive part? F max 0, which means the maximum of f and 0. And f minus, which is f minus is, what is f minus? It is just the positive part of negative f, which means it is minus f max 0, which if you want, there are multiple ways to write it. It is the negative of minimum of f and 0. Okay, so it's very simple actually. It's just for positive number. So it's, you can define it for numbers. Okay, positive, I mean, plus means when you put a plus on a number, it means either if the number is positive, you take the number, otherwise you make it 0. And if you put negative, if it's minus 1, okay, so let me write a picture here that will be clear. So if I have a, if this is my x-axis and I have a function like this, if this is my function f, then what is f plus? I'll write f plus in blue. F plus will be the function which is 0 here, okay? And it is the same as f here. Okay, so this is f plus. The blue part is f plus. Okay, and what is the f minus? Well, it is not this. Okay, if I take this, I am now marking something in green. Whenever it is negative, I take f, and whenever it is positive, I take 0. So if I do that, this is not f minus. What is this? What is this green part? It is negative of f minus. See, the way f minus is defined, f minus is a non-negative function. It is the f minus. So f minus would be the flip of this. Okay, so this thing is f minus. So this is the negative of f minus. Okay, so since it's the maximum of two measurable functions, so these are also measurable. Is it okay? Is the definition clear? It's the maximum of two measurable functions, hence measurable, and also non-negative. Both are non-negative because they are, I mean, by definition, they are non-negative. Okay, therefore, integral over x f plus d mu and integral over x plus f minus d mu are well defined by step 2 as numbers in 0 and plus infinity included. Okay, in plus infinity included. Now, how would I define what is how is f how do you recover f from f plus and f minus? By the way, okay, that I should have said they are measurable and non-negative. How do you recover f if I know f plus and f minus? How do I write f in terms of that?
F plus minus F minus.
F plus minus f minus is f. Okay, you take any point. If fx is positive, then this will be fx, this will be 0. If fx is negative, then this will be 0 and f minus will be the negative of fx because we take the positive value, and so minus will do the right thing. Okay, so this is clear, right? What will I get if I add them? Because that may be what one might think first. F plus plus f minus, what is this?
Absolute F.
This will be the absolute value of f. If you take f plus plus f minus, you see the top part here, that is just the absolute value of f. So the positive and negative parts will give you the function if you take the difference, and the absolute value if you take the sum. So how would you define the integral then? We are supposed to define the integral of f. So we look at this. You should take the integral of this minus integral of this. That's what you should define it as, right? So, but the only problem will be if both are plus infinity. Okay, so then we define integral x f d mu to be, this is the definition, as integral x f plus d mu minus integral x f minus d mu, provided both are not plus infinity. If it is plus infinity, then you cannot define it, right? You cannot define it. Or let me just yeah. So this one here, the convention is if plus infinity minus something finite is defined to be plus infinity, okay, and something finite minus plus infinity is minus infinity. That's the convention. Is this clear? I mean, I hope it's not confusing. See, we have these two, we take the difference. So if this is confusing, let me say the important point is when both are finite, then we can define the difference. Okay. So if both these integrals are finite, these are both well defined in the step 2. Okay. These are from step 2 because these are non-negative measurable functions. Then that is the most important case. We say that f is integrable. If you want Lebesgue, you can add the word Lebesgue, but let's just say integrable. That's going to be the default now. Integrable, and integral x is integral f plus d mu minus f minus d mu. Okay, so that's the most important case. If both f plus and f minus have finite integrals, their difference is what is we call integral of f, and in that case we say that f is in fact integrable. But it's kind of convenient. This is, you don't have to worry too much about this, but it's just a convenience that if one of them is finite and the other is infinite, we can define it to be either plus infinity or minus infinity without ambiguity. But if both are infinite, we cannot define. If both are infinite, we don't define. We say that f is not integrable. We don't associate any number to it.
Sir, so that means that fx equals x over all the reals is not integrable according to this definition?
Yes, definitely. Yes, it's not integrable. So you might want to say that it is 0 because it's an odd function or something like that, but it is not valid. It would mess up everything, all the properties of integration if you try to do that. So no, it is not integrable. Even fx is 1 by x is not integrable. One second. Yeah, just give me a moment. Just give me a moment. Sorry. Yeah. So okay. So right. So that's so this is the entire definition of Lebesgue integration. Okay. So first we define for simple non-negative measurable functions, very natural definition. Then we go to non-negative measurable functions, and we use simple non-negative measurable functions by saying that we define this as the supremum of all those values of the integrals of non-negative simple measurable functions which lie below f. And then we go to general measurable function and we break it into difference of two non-negative measurable functions. There may be many ways to define, break it into difference of two non-negative measurable functions actually. In fact, that is a question of ambiguity. But this is somehow a minimal way to break it into two. Let me not explain what is minimal, but where one is positive, the other will be 0. Okay, only exactly one of them is non-zero. So then this is the unique way to break it into two difference of two non-negative functions. So we do that and we take the integrals of those and take their difference. But taking difference can be a problem if both are infinity. Otherwise, we just take it. So that's all. So this is the complete definition of Lebesgue integration without knowing anything of the properties, how it behaves, etc. With just this, it won't work. We have to plug in a lot of steps in between to make a real sense of this. But are there any questions here? Is the structure clear? In one way, it is good to see it like this because the entire structure is clear. 3 steps, that's all.
Sir, here whenever we are telling measurable means Lebesgue measurable, right? And in real space.
No. Measurable means f is a function from x to r, right? All these functions are from x to r. So we take the Borel sigma algebra this side and f this side.
Okay, like that can be other than Lebesgue measure also.
Yeah, x is a very general measure space, any measure space.
Okay.
The special case is taking real line with the Lebesgue sigma algebra and Lebesgue measure. You can do that if you want. I mean, that is the special case. You can take Lebesgue or Borel, it doesn't matter. On the target space, it's always Borel. On the domain space, you can take Lebesgue measure. So you can take that RD with, if you take R2 with RD with Borel sigma, I mean Lebesgue sigma algebra and Lebesgue measure, then you get multiple integrals. I mean the double integral, triple integral, all that. So it will be a generalization of the usual double and triple Riemann integrals. So all those are covered here. Okay.
Yeah, okay. So what is this is a general space, not like in general that is not dealt with.
So we don't need that. I mean, so that's why it is a very general measure space. I make no assumptions actually. This is a fully general definition.
Yeah,
It
okay,
works in
thank you.
that generality. Yeah. Any other questions? So one of the things is, for example, a very simple example is actually. So just to give an example, summation is a special case of this, I said. So if you take, you can take another example is you can take Z with the power set and mu. What is mu is the counting measure. So here Z means any countable set. So mu of A is just the cardinality of it. For any subset of integers. When you take integers with the power set sigma algebra, so I can take A to be any subset of integers. Its measure is defined as the cardinality of the set. This is a measure, by the way. So if you have never done this, I don't know if I ever put this as exercise. Check that this is a measure. Okay, check that this is a measure. So what will be integration here? So if I give you, if f from Z to R, okay. So what is simple? What does simple function mean here? Then f is measurable, by the way, because it's power set on this side. Pullback of any set will be in the power set, right? So then f is measurable. So all functions into real numbers are measurable. There is no problem with that. Okay. So what is f? F is simple means. Okay, let's not worry about that. Let me just say what is the integration here. What is integration? I'll just tell you that integral of f d mu is same as whatever you used to think of this infinite sum. You already knew the notion of infinite sums, right? So this is same as that. But what about this condition here? Not everything is measurable, but this when is this? What is this condition that f plus and f minus have to be? It is same as if f is absolutely summable. So you will have seen this notion. F is absolutely summable means that this is finite. Okay, so that's what it means. So the integral is, I mean, the summation is actually a special case of integration, I mean, of our new integration. So summation is not just a motivation. It was definitely a motivation here. We started with summation, weighted summation, and went on to define more general integral. But exact summation itself can also be seen as a special case of Lebesgue integral on a measure space with a countable set and a counting measure. That's just a point to keep in mind. So you can use this. Actually, things we prove here will also be theorems about summation, which are not necessarily obvious even for summation. Some of the things we prove about interchange of summations, you would have seen that in basic calculus class, when you can interchange two summations and such questions. and you would have seen rather complicated theorems. One of the nice things about measure theory, well, you have seen all the bad things about measure theory. It seems very complicated, but one of the good things is that you can forget all those ugly theorems. You will have very beautiful, clean theorems which tell you when you can interchange summation in the limit, or a double summation when you can interchange the order of summation and all such things. Okay, so that's from this special kind of situation. Okay, but this is not germane to the issue, so let me just erase it here. So what we have to do now is to go ahead and justify, see what are the properties of this integral. Okay, so what we want to get to finally is the following statement. Okay, so that is where to do that we will have to do a lot of things. So maybe I even put down the final statement. So we want to get to prove the, so this will be a theorem that will come. So we start with a measure space X, F, mu, a measure space. Okay, so then 1, if F and G are integrable, and let's say alpha, beta are real numbers, then the linear combination alpha F plus beta G is integrable. And what is its integral? If I take this function alpha F plus beta G, if I integrate it with respect to mu, what should I get? Okay, based on if it was Riemann integral, you know what you would get, right? I mean, you would get alpha times the integral of x f with respect to mu plus beta times integral of g with respect to mu. Okay, so this is a statement that we want to prove. So this is called linearity. So linearity of what? Linearity of integral. See, the definition of, the fact that we use this kind of notation is historical. Actually, one could have, what is this integral? It is taking functions and giving numbers. So you could have given it a different name like I of f. Okay, integral of a function. It would have been natural to call it I of f for some. It is takes a function and gives you splits your number. So it's a functional, or it's a function from the space of functions to numbers, or from the space of integrable functions to numbers. So what we are saying first is integrable functions form a vector space, and this I is a linear functional there. I of alpha f plus beta g is alpha times if plus beta times ig. But historically we have always denoted integral by this thing, and also this I notation turns out to be not convenient because it doesn't indicate the measure. You can put a measure down here, doesn't really make it any nicer. So we are more used to this notation. So we are using this. But you should remember, so the linearity is of the operation of integration. The operation of integral takes a function and splits a number. That's a function from a space of integrable functions to real numbers. And that has this property of linearity. So what else does it have? It has another property. If f and g are integrable and f is less than equal to g everywhere, okay, this is everywhere, then integral of x is less than equal to integral of x g d mu. So this is called monotonicity. So one special case of this, I mean, I'll just write it here. In particular, if f is greater than equal to 0, then integral x f d mu is greater than equal to 0. Okay. So if you write it in this form, they are actually equivalent forms, so to speak. So this would be called positivity. You see why, I mean, right? But this and this are the same actually. See, from here you get this because you just use f is 0 and g is your f. Then integral f d mu will be greater than equal to 0. Okay. But you can go from positivity to this if you already know linearity, because this can be written as g minus f greater than equal to 0. So if you have positivity, you will get integral of g minus f is greater than equal to 0. But if you have linearity, integral of g minus f is integral g minus integral f, and therefore you will get the comparison between the integrals. So in the presence of linearity, monotonicity and positivity are the same. So maybe I just write it here. They are not two different properties, they are the same. And positivity are equivalent. So these are the most important properties of integral. Okay, so that integrable functions form a vector space. Integration is linear and positive. That is all it is actually. That is what integral is. Okay. Later you will see that if you have a class of functions, large class of functions, and you give any way of assigning numbers to them so that it is linear and positive, then it will be an integral with respect to some measure. That is one of the great theorems of measure theory. But we'll come to that later. So I'm just but this is where we want to get, and to get there we have to do a lot of things actually, because it's not obvious. But is it clear, the theorem? Is it clear, the statement? So this is where we want to prove. But you know, if you look at our steps, okay, so we have first for simple functions, then for non-negative measurable functions, then for general functions. So let us see, is it obvious to us? This kind of thing, is linearity obvious to us, for example? Well, even with simple functions, it requires a little bit of work to show that. But here you see, this is going to be the tricky part. Here we have, what do we do? Oh, sorry. In step 2, we are taking supremum. Now, there proving additivity becomes very difficult. If I take f and g two functions, let's say non-negative measurable, can I show that the integral of f, let's just not even use any scalars, f plus g is another non-negative measurable function. Is integral of f plus g equal to integral f plus integral g? Okay, this is actually not obvious at all because of supremum. Okay, so what you know is, so this is where we will need a lot of steps to get there, because you know what I mean. If it's not clear to you, let me make the point here. So if I have a subset of real numbers, so if A and B are subsets of real numbers, then, and I take C is A plus B, which is all sorry, this is not what I mean. Sorry. Okay, let me not say it in that way. Let me say it in the specific case. So suppose f and g, I am telling you the main difficulty that comes here in all this. If f and g are non-negative measurable, okay, so then let's h be f plus g. Okay, also non-negative measurable. So my question is integral h d mu equal to integral f d mu plus integral g d mu? This is the question. And this is actually not obvious. Why? So this is really in step 2. in step 2 we define this, right? So this is how you define the supremum. One way is kind of clear. Okay, so you take any s less than equal to f less than equal to 0, t less than equal to g less than equal to 0. Okay, s and t simple functions, simple measurable functions. Then 0 less than equal to s plus t less than equal to f plus g, and also s plus t is simple and measurable. This is not difficult. Okay, let me just maybe if I lost anybody, let me explain what I am doing. So I gave the definition of Lebesgue integral, which will proceed in 3 steps, and then I stated the goal. We want to prove that Lebesgue integral is linear and positive, okay, or linear and monotone, whatever you prefer. Since I have only about 10 minutes, so I'm not going to do all the steps. So what I want to say is that there are many steps one has to do between these to go from one step to another to really get to this final fact. And I'm just pinpointing, since I don't have time to do that, I will do that next class. Anyway, no hurry. I'm pointing out to you the key step which will be difficult. The key step which will be difficult, one of them, like Shekhar already pointed out when I asked this, will it be true that, I mean, so there are issues like if f is a step function, I have one definition here and I have one definition here. Is it true that they will agree? Yes, it will agree by if we prove monotonicity. That's actually not too difficult. But what will turn out to be the most difficult point is this, the linearity of this. It's not so obvious. So if one way is okay, that's what I'm trying to say. If f and g are two functions, non-negative measurable, and h is f plus g, the question is whether this is equal. Now, everything is, all three are defined as suprema of integrals of step functions, or sorry, not step, simple functions of step 1. Okay, so one way is clear. If s is less than equal to f, t is less than equal to g, s and t non-negative simple measurable, then s plus t is also non-negative simple measurable. Takes a little step to, I mean, it's easy to see because s takes finitely many values, t takes finitely many values. How many values can s plus t take? Finitely many values. So this will be a simple measurable function, and it will be sandwiched between this and this, which is h. Hence, integral h d mu will be greater than equal to integral s plus t d mu. Okay, so we will get this. Now, it's another thing that this is also a question. Is it true for simple functions that I can write it as integral s d mu plus integral t d mu? So this is a point that one has to justify. Need to justify. But once you justify that, now this is this we can choose s and t so that integral s d mu is greater than equal to, let's say, 1 minus epsilon times integral f d mu, because it's the supremum, right? Or let's write it as integral f d mu minus epsilon and integral t d mu minus epsilon. So I can do this. So I can choose s and t like that. Then this will turn out to be greater than equal to integral over x f d mu plus integral over x g d mu minus 2 epsilon. So, and since epsilon is arbitrary, we will see that integral h d mu is greater than equal to integral f d mu plus integral g d mu. More or less, if you understand supremum well, it would have been clear from just the straight definition. You would have seen this point that when you take supremum, one way additivity will hold, this subadditivity sort of, or superadditivity holds. Integral of h will be greater than equal to this. But what about less than equal to? that is really not obvious. So this is the most non-obvious step in the entire construction. Okay, so this is not obvious, and that is where all properties of measure, everything will come in there. Okay, and we will prove this. So, well, I won't just jump directly to prove this. So what I will start with next time is I will start with step 1. We will just take step 1, prove a few things about the integral as defined on simple functions, simple non-negative functions, then use that to upgrade those properties to non-negative measurable functions, and then use that to upgrade those properties to general measurable functions, which will get us to this theorem. Okay, so this is the map of what we will do next lecture. Probably I'll finish it next lecture. That will complete us the integration definition. Yeah, I think I will just stop here and take questions if there are any.
Sir, on a logistical front, what is the progress on the grading of the midterms?
0. Well,
Okay.
because I had, I mean, there were things I did not do anything. So my plan is to do it tomorrow also.
All right, not a problem.
Yeah. So 30th is what you said, right?
Right.
Yeah. See, well, I am still a student at heart in some way. I do things at the last moment. So, sorry about that, but I will do it. Tomorrow and day after is, I mean, tomorrow is what I plan to do. But if it gets slow, I may end up doing it also day after tomorrow. But as I said, if anybody requires it, please write me an email, okay? If anybody requires to be graded soon and wants to know for sake of dropping and so on, please let me know.
Sir, also, are you staying on campus?
No, I am not on campus, and I'm 10 kilometers away. So, but why?
No. I was just thinking that if you were utilizing the department's internet, then maybe we might have to reconsider and stuff. When to hold, how to hold.
Oh, why is that?
If you were using department internet, right? So because departments would be locked down and stuff.
Oh, I see. No, but if department is locked down, they will lock me out, not in. So
right. So that was precisely the point. So if you were using the department's internet on a regular basis, then maybe depending on your arrangements at home, we might have had to reconsider some things. But given that you're already at home, we don't have to do anything.
Okay, so you people will be in, many of you are in hostel and maybe some are at home, right? I mean,
some people are going
It's
home.
5 o'clock.
We don't know how many are remaining so far. We'll find that out in a while.
Of that, people at home, their situation hasn't changed, I assume. People in the hostel, you will continue to have internet, right? I mean, I don't know. The load may be higher because everyone will be in the hostel and taking classes. So the load may become higher, which may cause some issues. Who knows? We will see that.
It's not going to become too high, but yeah, I mean, it should not be a major issue.
Yeah, last year they were supposed to fix all this and increase all this, but I don't know to what extent that has happened. Yeah. But anyway, we can't help it. We will have to deal with it. If there are too many problems, then we will have to worry what to do about it. But let's not worry about it unless the problem arises.
True.
Yeah, but do point out if you are having internet problems next class onwards, and I mean even now, then let me know. Okay.
All right.
At hostel, it is not very. We don't have a very good internet.
In your hostel, is that so? So
yeah. Actually, I'm using mobile internet right.
Oh, really? I mean, so is it that way? I mean, you should get it. I mean, it's a problem for everyone. I mean, probably you should complain and get it fixed. No, I mean, they are saving a lot of money, by the way. You don't have to worry. I mean, I think just on electricity alone, IISc must have saved tons of money. So, yeah. So I mean, no, this is something they have to provide. If we are giving you online classes, it is IISc's responsibility to provide good internet in the hostels. So don't go alone. It's not a problem for you alone. Just get some other people and complain and get it fixed if possible. Yeah, don't hesitate to complain. I mean, these are facilities IISc is supposed to provide. So yours is what? A block, is it?
Yeah.
Huh?
Yes, yes.
A
A block, yeah.
Okay.
Actually, we have noticed that when internet is down in one block, it is down everywhere.
Oh, I see. Okay. But is it a problem that it goes down often, or is it generally poor?
No, not just. But let's say like